This is part 3 of a series on generative adversarial networks. In this video, we will look at deep convolutional GAN, shortly DCGAN. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the previous videos, we looked at the architecture of a standard GAN and used it to generate two-dimensional data. In this video, we will look at the architecture of DCGAN and use it to generate MNIST images. DCGAN was introduced in 2016 by Alec Radford, Metz, and Soumith Chintala in their paper Unsupervised Representation Learning with Deep Convolutional Generative Adversarial Networks. DCGAN, as the name suggests, is a type of GAN model in which the discriminator and generator are composed of convolutional neural networks. DCGAN generator consists of a series of 4 fractionally strided like this, which allows it to produce higher resolution images. Fractionally strided convolution is also called transposed convolution. The architecture guidelines for DCGAN presented in the paper are as follows. And the detailed settings for model training are as follows. The DCGAN generator takes as input a random noise Z vector of size 100, passes it through 4 fractionally stride convolutional layers, and outputs a fake image GZ of size 64 by 64 by 3. Notably, no fully connected or pooling layers are used. In this video, we will implement a small version of DCGAN that outputs MNIST images of size 28 by 28 by 1 as follows. The architectures of the discriminator and the generator models of the DCGAN we will implement are as follows. These architectures are taken from Chapter 4 of the book, Advanced Deep Learning with Keras by Roel Atienza. The discriminator takes as input an MNIST image of size 28 by 28 by 1, passes it through 4 2D convolutional layers, and finally outputs a scalar value in the range 0 to 1. The input is either X or G of Z. That is, the discriminator performs binary classification. The generator takes as input a random noise Z vector of size 100, passes it through 4 2D transposed convolutional layers, and then outputs a fake image GZ of size 28 by 28 by 1. Batch normalization is applied to the output of each transposed convolutional layer. Here, none is the mini-batch size of the input data. Now, let's implement a small version of the DCGAN model that generates MNIST images. Load the MNIST dataset. We will only use 10,000 NIST images. Build a discriminator model, create an input layer, and add 4 2D convolutional layers to it. We use the leaky ReLU activation function as mentioned in the architecture guidelines of the paper. The output layer uses the sigmoid activation function for binary classification. Create a D model. Next, we build a generator model. Create an input layer that will receive a random noise Z vector of size 100. We transform the Z vector into a tensor of shape 7 by 7 by 128 by performing linear projection and reshape. Then we add a series of 4 transposed convolutional layers. We apply batch normalization and real U activation function to the output of each transposed convolutional layer. The final layer applies the sigmoid activation function to generate MNIST images. In the paper, the data was scaled to the range of -1 and +1, and then the hyperbolic tangent activation function was used. Since the data we are using is scaled to the range of 0 and 1, we use the sigmoid activation function here. Create a G model. Next, we write a class that creates a DCGAN model. This class takes a discriminator and a generator as input. The DCGAN model includes a discriminator and a generator model. This is a custom model created by subclassing Keras model. This class is almost identical to the one we used in the last video. For more information about Keras custom model, please refer to this site. First, let's write a function to compute the loss of the discriminator. The inputs to this function are real data X and random noise Z. When Z is input to the generator model G, GZ is output. When X is input to the discriminator model D, DX is output. When the output of the generator, GZ, is input to the discriminator model, DGZ is output. We clip the output values of D to prevent the loss from becoming NaN, or infinity. We compute the loss of the discriminator using this formula. Instead of maximizing positive loss, we minimize negative loss by returning negative loss. Next, let's write a function to compute the loss of the generator. The input to this function is random noise Z. Use this formula, or this formula, to compute the loss of the generator. We will use the second one. We define a list of metric objects for the discriminator loss and the generator loss. And we define the train step method. We implement algorithm 1 presented in the paper. The mini-batch size is M. First, we update the discriminator. We use the number of K steps as 1. Sample mini-batch of M-noise samples Z from a uniform distribution. Update the parameters of the discriminator to minimize loss D. Next, we update the generator. Update the parameters of the generator to minimize loss G. Finally, we update and return the metrics to later see how each loss changes during training. Now we create and compile the DCGAN model. Fit this model to the real data. The mini-batch size M was set to 200 and the number of epochs was set to 100. Observe the changes in D loss and G loss during training. Finally, we use the trained generator to generate MNIST images. Let's check the results. The changes in D loss and G loss during training are as follows. The loss history of the discriminator is like this. And the loss history of the generator is like this. The images generated by the generator are as follows. Images of various digits were generated. However, if the number of epochs is too large, mode collapse may occur in this model. The images generated by the generator when the number of epochs is 1,000 are as follows. You can see that a lot of images of digit 1 are generated. The images generated by the generator when the number of epochs is 1500 are as follows. You can see that a lot more images of digit 1 are generated. This is the two-dimensional Z-space of the MNIST dataset generated by an autoencoder. These images probably come from this mode. So we can see that mode collapse is occurring in our DCGAN model. Let's run this code. We got the following results. In the next video, we will look at unrolled GANs, which can reduce model collapse.